Good afternoon, everyone. It's a great pleasure for us to have this joint talk between Charles Park and OTFS-SIG. Good afternoon, everyone. It's a great pleasure for us to have this joint talk between Charles Park and OTFS-SIG on some for the online seminars on waveforms. And today we are very glad to have Professor Ana Armada from Spain to give us the presentation on the constant envelope multi-carrier waveforms for 6G. And Professor Ana is an IEEE fellow, and she is currently a professor at Universidad Carlos III de Madrid, Spain, where she is leading the communication research group. She has been a visiting scholar at Stanford University, Bell Labs, and the University of Southampton. She has participated and coordinated a large number of national and international research projects, as well as contracts with the industry. She is the co-author of 8 chapter books on various communications and signal processing. She has published more than 300 papers in international journals and conference proceedings, and she holds 7 granted patents. She is serving on the editorial board on IEEE Open Journal of the Communications Society and the ITU Journal on Future and Evolving Technologies. She has been the chair of the IEEE ComSoC Signal Processing and Computing for Communication Technical Committee and the vice president of member and global activities of IEEE ComSoC, where she is now the vice president of the conferences. She has been awarded the 3rd place Bell Labs Prize for shaping the future of information and communications technology. She has received outstanding service awards from IEEE ComSoC Signal Processing and Communications Electronics Technical Committee and the IEEE ComSoC Women in Communications Engineering Standing Committee and the IEEE ComSoC and KICS Elementary Global Service Award. So thank you very much, Anna, for joining us today. And without further ado, please join me to welcome Anna for today's speech. Thank you.
Thank you very much for your kind introduction and for inviting me to give this talk about this topic that I really like a lot. That is constant envelope multicarrier waveforms. And I'm going to tell you a little bit my view about these waveforms. But first, I would like to start by talking about 6G and why do we need any changes in the waveform for 6G. So, as you probably know, there is already a document from the International Telecommunication Union that is telling us what they are foreseeing to be IMT 2030, that is going to be the 6G. And there is already several usage scenarios and constraints where we are seeing where we would like to go. And what do these scenarios tell us or require about the waveform design is something I want to point out. So let's first have a look at several new things that appear around the scenarios that are completely new, like, for example, sustainability. For the first time, we are going to really take a lot of care about the energy consumption. And if we care about energy consumption, there is one characteristic of the waveforms, that is the peak to average power ratio, that is going to be extremely important because we want to be efficient in the amplification. Now, another thing that happens to be around is the connecting the unconnected. Again, something probably new, a new focus. And here, if we want a complete coverage of all the world, one thing that is a key ingredient is the non-terrestrial networks. So we want the satellites and the drones to fly around and be able to go to several locations. And these usually also have very stringent requirements about amplifiers. So again, bringing us the problem of the PAPR. Plus another problem that is the time variability, because they are going to be flying around quite fast. Also, if we really want to connect everybody, there are rural areas, there are people that live a little bit farther from the main hotspots. So we need some waveforms that are going to guarantee wide coverage. And this again has an implication of the PAPR. And of course, we need low complexity because we want everybody to be able to buy these new technologies. Now, if we look at what are the new scenarios that arise together with an extension of the classical 5G ones, we can see that, for example, there is immersive communication. Immersive communication means bandwidth because we really are going to be needing a lot of data rate, and this data rate, we usually are going to find the needed bandwidth by going up to higher frequencies, where once again we are going to find the problem of the PAPR plus phase noise, other kind of problems that are associated to hardware when we go to higher frequencies. Additionally, if we want immersive communication, that means we want to fully experience all kinds of senses, of human senses. We want to be immersed. We need a very low latency. That calls for short symbols, that is the opposite to what we have been usually doing with OFDM. And if we really want to be immersed, we need to sense what is around us. So we need to be careful with the channel estimation and try to combine sensing with communications, what is usually called ISAC. What else I see here? I see the high reliability, low latency, again, low latency short symbols, and we see also the massive communication, where we mix with MIMO. And based on all this, we can, for example, make a wish list. So what would we like from the waveform in order to be able to fulfill all these things that 6G is calling for? And we have several characteristics that the current waveform in 5G, which is OFDM, is already fulfilling. So it is very robust to multipath. It has a very easy implementation through the fast Fourier transform. It is very easy to combine with MIMO because of the orthogonality. And it has also the capability to very easily multiplex a lot of users with the time domain, frequency domain scheduling. However, there are a few more things that this OFDM signal is not good at, that I mentioned, like the phase noise, like the PAPR that is extremely high. It's also not good when we have time variability, and it doesn't have, in general, short symbols. And another thing is not a problem, but it needs to be developed. How we use it, and usually we use it for communications, but we need to see how to use it for sensing. So I'm going to focus at the beginning on one of these characteristics, that is the peak to average power ratio, while the others somehow will come into the picture while we walk through what are these possible waveforms. So let's have a look at the PAPR, and let's try to find multicarrier modulations that are constant envelope. Why constant envelope? Because if then we can really amplify, at full power. What is the state of the art? Well, we all are aware of some modifications with some pre or post processing of OFDM that improve their characteristic of peak to average power ratio. And in particular, there is the single carrier FDMA, also called DFT spread OFDM, that is the one that is used in the uplink of 4G, and also optionally in the uplink of 5G. So what is this modulation? It starts with a classical OFDM. So if we look at from this point of view, if this is a signal we are transmitting and this is a signal we are receiving, what we have here is an OFDM transmitter and receiver. But the thing is, before that, we do a spreading with another FFT. And of course, we will do the IFFT at the receiver. So if we really take a look at what we are doing at the transmitter, if we are doing an FFT and immediately an IFFT, that means we are doing nothing. So if our signal originally is single carrier, our signal after this processing will still be single carrier. Well, that would be very nice, but the fact is these M and N, that are the sizes of these FFTs, are not the same. If they were the same, we could just not do anything. But if we don't do anything, we don't have any multi-carrier signal, right? But since they are not the same, at the end of the day, this signal is not really single carrier. Depending on how we choose M and N, we are going to occupy different bandwidths. So this is easy to multiplex against several users, but what we get is really not single carrier. It's not as bad as OFDM, so we are going to save a few dB, I mean a substantial amount of dB in PAPR, but still, we still have limited problems with the amplifier. So logically, we can ask ourselves, this is not constant envelope. Can we have a multi-carrier modulation that is truly constant envelope? And actually, there are two. There is constant envelope OFDM that has a few modifications to the classical OFDM transmitter and receiver, where those are here highlighted in purple, that it's just a few blocks could be added to the classical OFDM. And we have a frequency modulated FM-OFDM that, to what we have in CE-OFDM, adds a few more blocks that I'm showing here in green color. So what are the advantages of these modulations? They are completely, truly constant envelope, so very friendly to the nonlinear amplifiers, but they are still OFDM. So we can still do the frequency domain, time domain scheduling and other nice characteristics of OFDM, we can still keep. And also the processing is just adding a few things to our classical OFDM. So let's go a little bit more to the details and see how these waveforms look like and how we can obtain them. So first, let's have a look at the constant envelope OFDM. So what are we doing here to have a constant envelope signal is, first of all, we are going to need to make sure that our OFDM signal is real. Why? Because we are going to put that into the phase of a carrier. So we need a real signal, and to do that, we need to sacrifice a little bit the bandwidth, because we are going to use half of the subcarriers to ensure this hermicity of the signal. So here, after the IDFT, it is going to be real. This is one disadvantage that we are going to have in CE-OFDM. After that, what we are going to do is modulate the carrier in phase. So we put this into the phase modulator, and well, we can have a parameter here that is the modulation index that is going to scale this time domain OFDM signal to higher or smaller amplitudes before the phase modulator, and this allows a little bit of a trade-off between performance and bandwidth. So this is going to give us the signal that we are going to transmit, and then when we get to the receiver, sorry, it's just here, we are going to perform the modulation of this phase, angular modulation with a phase demodulator, that is an arctangent. And we need to be a little bit careful, because multiples of 2 pi appear as the same phase, but maybe originally the signal was not the same. So there is a need here to do a little bit of unwrapping to make sure that we actually get the original phases. But after that, we have the normal DFT, and we continue with our information. So as you can see here, it is just this phase modulator and demodulator that are added to the usual OFDM, plus this need to ensure that our signal is real. And with that, this new waveform has a few pros and cons. Let's examine it. I already mentioned, this is an important one, we are going to lose half of our subcarriers because of this need to make the OFDM signal real. This is an important con. Another thing that I didn't emphasize, I will emphasize next with the next waveform, is since we have a nonlinear phase demodulator, then the classical channel state information obtention before, in the frequency domain after the DFT in the receiver is not going to work. So we need to think of other ways of obtaining this channel state information. This is not impossible, it's just we need to think how to do this. Another thing that is an important disadvantage is that now, after this nonlinearity, if we have the additive white Gaussian noise at the receiver, it is no longer being with the same, distribution. And many channel coding techniques are based on assuming that you have AWGN. So we need to rethink a little bit how we code and decode the channel coding. And there is also another characteristic typical of angular modulations, that is the threshold effect. And this is not so serious because there are threshold extension techniques that can be used. But what that means is from an SNR below a certain threshold SNR, the signal doesn't work well. And after this, it works very well. But like I said, there are techniques to extend this threshold. In this technique, we didn't solve at all the sensitivity to rapid channel variation. So this is also a disadvantage. But we have a big advantage, that is the long range high coverage, because we can amplify at full range. Well, it is a very important advantage, but there are a lot of disadvantages here. So let's have a look at the other waveform and see if we can kind of solve some of those. So this is FM-OFDM, and it is very similar to constant envelope OFDM. So again, we have here the complex phasor, so an angular modulation. So again, we need our signal to be real after the IDFT. So we need the conjugate symmetry in our modulation. And what we are going to do is, before putting this OFDM information into the phase, we are going to have this addition of the samples. So instead of driving the phase, OFDM here is going to drive the frequency. And then we again put this information into the phase of the carrier. Once again, when we go to the receiver, we need to extract the phase, similarly to what we do with the CE-OFDM, and we need to do kind of a differential demodulation here to extract the frequency from these phase variations. And also there is something new here, that is the cutoff subcarrier, that I'm going to explain next, because it turns out by nulling a few subcarriers close to DC, sometimes even one, we are going to get a very, very good performance. So with FM-OFDM, not only we get constant envelope, but also we get a very robust signal against the fast channel variations. So Doppler and phase noise are completely avoided with, as I mentioned, a cutoff frequency, because they are confined to the lower subcarriers of the spectrum. So depending on how large our Doppler and our phase noise are, just with a few subcarriers, usually with one, just leaving it without modulation and getting rid of it, all these effects are absorbed there. So we can overcome phase and frequency impairments without even needing to estimate the channel at all. And this happens if we have flat fading channels. Of course, we sometimes have flat fading or very close to flat fading, meaning with very small delay spread, for example, when we are using an narrow beamforming. But some other times we are going to have frequency selective channels, and if this is the case, then we need to estimate the channel state information, as we usually have to do also with OFDM. But with the particularity that we need to think of new ways to estimate this channel, usually in the time domain, before the nonlinearity comes into play at the receiver, because otherwise, the convolution and everything is not fulfilled. So FM-OFDM still shares some of the disadvantages that I mentioned for constant envelope OFDM. For example, the bandwidth loss, and for example, the need to think how to estimate the channel. And for example, they need to think how we do the channel coding. And the threshold effect that, like I mentioned, can be solved. However, it is very robust to rapid channel variations, and again, has the advantage of being able to be used in long-range high coverage. So here we have some disadvantages, but we have very substantial advantages. So how do these new constant envelope modulations perform when we have a nonlinear amplifier? We can see here in this graph where in the x-axis I'm showing the output back off of the amplifier, and here the total degradation that we are going to experience. And OFDM, as you very well know, needs quite a big output back off, and actually the total degradation, meaning what is the SNR we are losing because of the output back off plus the needed SNR for the modulation, is quite big. And of course, DFT spread OFDM improves substantially, so there are a few dB improvement, but still is far away from the zero degradation that you can get with a zero output back off with FM-OFDM and constant envelope OFDM. That would be the sweet spot here. So this is what makes these constant envelope modulations quite interesting for some particular scenarios. So not only this, in particular in the FM-OFDM, you have other advantages like I mentioned. And if the channel changes very fast as even changing within an OFDM symbol, FM-OFDM is extremely robust. So you can see here what would be the bit error rate against the SNR. And we can see that cyclic prefix classical OFDM is going to fail for 1000 kilometers per hour and also for 250 kilometers per hour. Constant envelope OFDM is a little better, but still not very well performing. But FM-OFDM really performs extremely well. In this particular case, the channel is flat. So in FM-OFDM, we are not doing anything, no need for any equalization. And it can even get some advantage of very fast channel variations because there is a little bit of diversity that it can be gained when the channel changes very fast. So this is interesting, and at the same time, we can have a look at the phase noise. And in this case, what we are using is some phase noise characteristics that are recommended by 3GPP for the different frequencies. If you go up in frequency, the phase noise characteristic is much stronger. And here we are looking at what happens again with constant envelope or cyclic prefix OFDM. And even if we do some ideal channel estimation, this phase noise is having a very detrimental effect. But on the other hand, in FM-OFDM, without any channel estimation or equalization at all, we can see that it's extremely robust to phase noise, even to the very high phase noise that we get at 300 gigahertz. So, okay, this can be interesting, for example, like I mentioned, for non-terrestrial networks, because in non-terrestrial networks, in the LEO satellite, you're going to have a combination of fast speed, phase noise, and a nonlinear traveling wave tube amplifier. So they are exactly the characteristics where FM-OFDM is going to be extremely robust. And we can see here in some simulation with a 3GPP channel for these non-terrestrial networks that FM-OFDM, again, has a very good performance as compared to other possible multicarrier waveforms. So in principle, this makes potentially interesting these two waveforms for future 6G. And I want to have a look at what are these potential 6G new emerging scenarios and how is the performance of these waveforms in these scenarios. So what scenarios I'm talking about? I'm talking about three different scenarios. One of them is a sub-terahertz radio link that is going to happen at quite high frequency, 140 gigahertz. And of course, in this high frequency, we will have a big bandwidth, but at the same time, to have a reasonable number of subcarriers, we will need also a quite large subcarrier spacing. And well, here you have a summary of the characteristics that we're going to use, channel models from a European project EXA-X, and also some characteristics. In this case, we are going to not have any Doppler because we assume it is static, but we will have other impairments like phase noise and channel. In the non-terrestrial network, we are going to look at two cases, a GEO satellite in S-band and a LEO satellite in Ka band, different frequencies, again, also different subcarrier spacings, but more conventional, more closer to what we have in 5G. And also, well, here you have more details about what are the channel models that are recommended for these cases. And here we're going to have the velocity of sometimes of the UE, on other times not the UE, but the satellite that is going to create some carrier frequency offset and due to the Doppler. So let's have a little bit of a look at what happens in this scenario. So for example, in the terrestrial link at sub-terahertz band, what we are going to have problematic is the high power amplifier. That is for sure going to be nonlinear and at the same time a high phase noise. And this is going to be a dominant impairment that is going to have a common phase error and intercarrier interference in OFDM. And because of that, we can see that classical OFDM or even constant envelope OFDM are not going to perform well. But on the other hand, FM-OFDM, with or without the high power amplifier, is going to perform extremely well because it is robust to the amplifier and the phase noise that are like the main two impairments in this user case. So, like I said, FM-OFDM consistently outperforms the other waveforms in this particular case. Now, in the GEO S-band satellite, we are in the model that we are using, recommended by 3GPP, phase noise is negligible, and Doppler shift spreads are moderate, and the HPA nonlinearities are very strong because we have a GEO satellite. It has to really amplify powerfully. So let's have a look here at what we see. And we see again here the classical OFDM. Constant envelope OFDM is a little bit better, and FM-OFDM is again the best. So constant envelope OFDM here shows a better performance because here the nonlinearity is the most important problem. There is no phase noise, but again, FM-OFDM, we can see that it even improves. And what about the LEO Ka band? Here, there is again the nonlinear amplifier, and here the Doppler is going to be severe, and the phase noise. So we have a very similar situation as compared to the previous cases. There is more distance from the FM-OFDM when we don't equalize at all as compared to what would be an ideal FM-OFDM because there are several channel impairments, but again, FM-OFDM is really robust even without any kind of channel state information and equalization. So, well, I hope I convinced you that this is interesting, but anyway, even if in these examples we didn't need to estimate the channel for FM-OFDM and also perhaps constant envelope OFDM, the reality is often we are going to have channels that are indeed frequency selective. So let's have a look at how we can estimate and compensate the channel for these new waveforms. So I want to recall that there are two ways essentially to perform the training to obtain channel state information in OFDM or in general in multicarrier waveforms. So the more classical scheme, usually called the PSAM, pilot symbol aided modulation, is where you classically have in your OFDM the frequency and time grid, but you reserve a few resources in time and frequency where you are not transmitting data and you are transmitting your pilots. And with these pilots, you can estimate your channel in the frequency time domain and do the equalization and compensation of the channel, usually in the frequency domain. But like I said previously, this is not going to work for constant envelope and FM-OFDM because you have nonlinearities in the receiver before performing the fast Fourier transform. So you need to somehow design ways to estimate the channel in the time domain before you do the FFT. However, there is another technique that is called superimposed training. Superimposed training meaning you are going to have your data everywhere in your time and frequency grid, and also your pilots everywhere in the time and frequency grid. So there is interference between the pilots and the data, and you need to design techniques to make this interference disappear somehow or compensate. A possibility to do this is based on assuming and knowing that your data are going to be uncorrelated, performing some kind of averages. But these new waveforms, CE-OFDM and FM-OFDM, may also suggest other ways to superimpose the pilots because they have a different structure in the spectrum as compared to OFDM. So for example, let me tell you an example for a superimposed training for constant envelope OFDM. And this is what we call a phase domain injected training PIT. And what we are doing here, we are injecting some phases in our phase modulator, because since our modulation goes only in the phase of the carrier, we can also alter these phases with a sequence of pilots that are just phases. Being phases means they are not taking any power out of the data, so the overhead in terms of power is 0, but of course, since they go together with the data, we need to find ways to get rid of the mutual interference. So we directly embed these pilots into the phase of our transmitted signal, and when we get to the receiver, we do some averaging to eliminate interference from the data and extract the pilots. And we are very lucky because for the structure of this phase modulation that is only, changing the phases of the carrier based on what happens when you average, when you have the mean of a cosine and a sine, and the noise that is also 0, we are going to find that actually when you perform this average, you are going to get some signal that is the pilot, modified by some term that is deterministic, that you can know. So at the end, what you get is the pilot, and you get rid of the data. And based on that, you can estimate your channel. And of course, once you know your channel, get rid of the pilots with the channel and the modulated data. So this is just an example of things you can do differently to have as minimum overhead as possible of your pilots with this constant envelope OFDM, and this PIT can also be applied to FM-OFDM. What is the problem here? This is not usable, not suitable for fast changing channels, because this average you need to do over a substantial amount of time where the channel should be static. Otherwise, you don't get rid so much of the interference. So this is a little bit a problem. But if you can have this possibility to average amount over a sufficient number of time slots, you can get very nice performance. So here you can see the achievable rate in black of what we would get with perfect channel state information, and extremely close what we get with this PIT technique, when we are able also to design the best way we can our PIT sequences. If the PIT sequences are not so good, then we are going to be a little bit farther away from this perfect performance. So this is one example. Another example is Some of these multicarrier waveforms have a different spectrum from the classical OFDM. And some time ago, we were having a look at a different multicarrier waveform, the filter one, that is called cyclic block filter multitone. And we realized it has some spectrum holes. So why not to pour your pilots in the places where your signal has lower spectral strength, right? Well, we did that for this particular modulation, but now recently we were looking at FM-OFDM and we realized it has a very similar spectral characteristics. So once again, why not? We can pour the pilots in these extremes. And with this idea, I'm going to show you in brief that you can completely build a scheme for estimation and the modulation of your FM-OFDM. But before that, let me just mention that even if I'm not going to focus on this, superimposing the pilot gives you complete freedom to do whatever you want with your pilots, because they don't need to be confined to any particular orthogonal resources. They can go everywhere. And we have some interesting work where we design these pilots for estimation of the channel in the delay Doppler domain, where you can also do a lot of things. However, I'm not going to focus on that today. Maybe we can talk about this some other day, because I'm going to continue with FM-OFDM, where we are just doing the classical processing in the time and frequency domain. So, how to design the pilots for FM-OFDM? And actually, these pilots and the way to cope with the channel that I'm going to present can be used also for any other kind of multicarrier modulation, provided they have zero padding. And later I will explain why it is important that you have this zero padding. So we have, in general, these doubly dispersive channels that are both frequency selective and are also fast varying in time, which are problematic. And if we have FM-OFDM, we must estimate and compensate the channel because of the frequency selectivity. So we designed these two kinds of pilots. One kind of pilot that is going to be like a column here, that is wideband. We call it the wideband reference signals, and these are going to allow us to estimate the multipath delays. And because the delays are going to change slowly as compared to other characteristics of the channel and the signal, we can have them from time to time, not very often. So we can wait a long time before we repeat these pilots. And at the same time, to track the fast changes of the channel, we need some narrowband pilots, some narrowband reference signals that we're going to put to the extreme of the signal, because, like I said, if you put them there in FM-OFDM, they don't interfere with your data, so you don't need to put any guards or things like that. But if you are using OFDM, then yes, then you will need to have some guard interval here and be careful with your data. So how can we do with these two kinds of pilots to estimate and compensate when you have doubly dispersive channels? I'm going to show you without going too much into the details. If you want, you can have a look at this paper that is going to explain all the details. But in general, this is applicable to zero padding OFDM, zero padding constant envelope OFDM, and FM-OFDM. And we are going to approximate this linear time varying channel as a sequence of piecewise linear time invariant channels. So small segments of the channel that are going to be constant. And then we're going to estimate each of these segments of the channel using the pilots that I already explained. And once we have them, we can do a classical single tap frequency domain equalization for each of these small segments. We process these segments independently, and then with some smoothing window, we are going to add all these signals. So let me just give a few details about that. Why do we need the zero padding? We need the zero padding to maintain the circular convolution, even if the channel is changing fast. Because if you have your classical OFDM with a cyclic prefix, but the channel changes very fast, at the end of your symbol, you are not having the same channel as at the beginning of your symbol. So even if the cyclic prefix is repeated, the channel is not, so you don't have this circular characteristic. But zeros keep being zeros no matter what. And because of that, you can maintain this. So this is important. And once you have your channels, your tap of your channels, because it's going to be a multi-tap channel, that are going to be changing in time. So this represents the time, and each of these is your channel tap. Each of them is changing with time, but we're going to design some segments as small as needed so that you can consider each of the taps constant in each of these segments. How many segments you need? Well, you have an equation that is going to tell you what is the error that is going to be at the end, interference that you are going to incur depending on how many of these segments you use. That is very related to how is your Doppler and your symbol time. So this is the key, to estimate each of these small segments, and we are going to estimate them with the pilots that I mentioned. First, we are going to do an overlap analysis. So we are going to put the last part of the symbol at the beginning to make it circular. And then we are going to do a classical LS estimator, where we're going to obtain a matrix that contains all these little pieces of the LTAP time domain channel. And well, just with an LS estimation where this is going to be related to our pilots and this is going to be related to our received signal, we can obtain this matrix. There is a little bit of processing here, but I don't want to explain too many details. You can have a look at the paper. Sometimes what happens is this pseudo inverse is difficult to obtain, because when you have a little number of pilots, very little, this matrix turns out to be ill-conditioned. So in these cases, what we recommend is to use some regularization, like a Tikhonov regularization, for example, to be able to perform this pseudo-inverse. And then once you can do this, you are obtaining your channel information in the time domain, and you can get your frequency domain response by doing a fast Fourier transform. So when you have all these piecewise constant channels in the frequency domain, you perform an equalization for each of them, which this channel coefficient that you have already obtained. And for each of these pieces, you're going to add them all, but with some window. So here you will apply some coefficient, some window, to make smooth the transition, and then you can have all of them together. So this processing, of course, is a little bit more complex than pure OFDM. You need in parallel as many single tap equalization steps as pieces you have in your channel. So if your channel changes extremely fast, you may need a lot of them. But in general, in our simulations, we didn't need to do a lot, because, well, at the end, the channel changes fast, but not extremely fast in real applications. Like, for example, here we can see with an example of a channel that changes at 120 kilometers per hour. We can see a comparison of FM-OFDM with the typical cyclic prefix OFDM that is going to work pretty bad, and with OTFS. And in OTFS, we present a couple of examples. One is the OTFS with a very, very complex DFA, decision feedback equalizer, and another one with a less complex MMSC equalizer. And things we can see here is in QPSK, we have FM-OFDM performing very close to OTFS with MMSC. And if we go to higher order modulations, FM-OFDM starts to get closer to the much highly complex OTFS with DFE, and even it gets better when you have a very high order modulation. Of course, to very, very extremely high order modulation, that 256, you really cannot do this in high speed environments, because at the end of the day, you are still going to have some imperfection. So this is interesting. And I mentioned that in FM-OFDM and in constant envelope OFDM as well, you can have some trade-off between performance and spectral efficiency. In part, this can be seen by the number of useful subcarriers. So how many of the subcarriers are really carrying data? So if you can have only a small number of them, the performance is going to be extremely good. On the other hand, if you want to have more subcarriers with data, the performance is going to deteriorate a little bit. So there is a trade-off here, in particular with, again, fast changing channels. And the impact of the velocity, you can see here, and I already showed other examples, that you can go very fast. So here we put the extreme of 2,000 kilometers per hour, and in 2,000 kilometers per hour, there is clearly a degradation, but still manageable. And for other speeds, FM-OFDM with this piecewise equalization performs very well. However, in all this, I'm showing you what happens when you have ideal channel estimation and piecewise equalization. If your piecewise channel estimation is real, not ideal, you can see here a degradation. This would be the ideal one, and this would be the real one. And you see there is a degradation of about 3.4 dB with respect to ideal. So this scheme is not perfect, and I'm sure there is still room, for improvement. Okay, so now I hope I show you that there are several advantages in FM-OFDM and constant envelope of OFDM, and also that there are ways to estimate channels, improve the performance, but there are also several disadvantages that I pointed out that are still there. So unfortunately, there is no, or at least I cannot find a waveform that fits all kinds of scenarios. If we compare the classical cyclic prefix OFDM with these two constant envelope waveforms, constant envelope OFDM and frequency modulated OFDM, we are going to see that each of them has pros and cons. Like, for example, if we look at the robustness to multipath, OFDM is clearly very advantageous if you have multipath, because you can do the frequency domain equalization and it is extremely simple. While for these other two, it is not impossible. I show you that it can be done, but it is more complex. If we talk about waveform that is low complexity, I think the three of them, if we don't count on this special channel equalization, the three of them are quite simple because they are based on FFT with a few blocks, and these angular modulations can be done very easily. There are specific chordic blocks that can perform them like with very low complexity. Now, talking about how to schedule multiple users and how to do the MIMO, OFDM is extremely simple for that due to the orthogonality of the subcarriers. In this other case, it's not impossible for sure. It's just it has not been researched enough. So I haven't seen schemes that do this multiplexing. Multiplexing the users is easy. What is maybe more difficult is multiplexing the reference sequences, the pilots. And this, I haven't seen this yet. However, when we look at the amplifier, clearly OFDM has a problem, while these two are very advantageous. And again, when we have the robustness to fast time variability, OFDM fails. Constant envelope OFDM also fails. However, FM-OFDM is very good. I also pointed out at the beginning that we need to do some sensing, and how easy it is to sense and to obtain the channel state information. In OFDM, it is fairly easy, while in the others, I already explained, there are techniques, but maybe they are a little bit more complex, or they may need a little bit more of research. The good news is that all those that I marked with something that is not positive but not negative, kind of neutral, they can be improved through some more research. So there is a lot of research to be done here, not only in a constant envelope multicarrier waveform, but in other waveforms that OTFS, ODDM, many others that share this architecture or of IFFT, FFT, and are very easily to combine with a classical OFDM. So I think what we need to be is flexible, and we need to allow for different waveforms and pilot structures within a common framework that can be a multi-carrier general architecture. I didn't say much about other waveforms, like I said, and also the important combination with MIMO. I want to point out there is a new project that we are starting, a European project called Multiplexing 6G, that is going to start very soon. And I just encourage you to have a look at the advances in this project, because we are going to work in a very nice consortium to further, advance in all these kinds of waveforms, and also waveform processing in all kinds of domains, including the spatial domain. I mentioned a few publications here and there while I was talking, and here I put you a summary of those that are more related to the techniques and the waveforms I explained. And with that, I want to thank you, and please don't hesitate to send me an email anytime you want to discuss or have questions about this or related techniques. Thank you very much.
Thank you, Vanna, for the great presentation. And it's appeared to me that this constant envelope waveform is actually coming back again. I have a few questions that I hope that I can get you answer. So you have mentioned quite a lot on the importance on the constant envelope. And yeah, in my opinion, it's actually not a new topic anymore, because there are waveforms such as CPM, continuous phase modulation, and there are other variations on OFDM, as you have mentioned. I wonder, what do you think of the evolution on continuous constant envelope waveform in general? Why we are not using CPM anymore? Why we need to use new constant envelope waveforms? Thank you.
Yeah, thank you very much for the question. I think the key is the broadband operation, multipath, etc. Right? That is a weakness for the classical CPM, that is narrowband, and in narrowband it works well, but when you go to broadband, then you have all kinds of problems that are solved with OFDM. And that's why I think an evolution of keeping the advantages of OFDM is very important.
Mm-hmm.
Not only its performance with the multipath, but also the way to multiplex several users with the frequency time domain equalizer. Those are advantages that have been developed with time and that we master today, and we don't want to give up, right? So that's why I think maintaining the multi-carrier structure is very important. Mm-hmm. Having said that, for low complexity narrowband scenarios that also are going to happen, mm-hmm. IoT and things like that, it is important to go back to other kinds of modulation that not necessarily are multi-carrier, and think about this, because I think we have been following a trend that was very successful to go to higher data rate.
Yes.
But now we still for sure need in some applications higher data rate, but it is so important to have low complexity, to be able to get to everywhere, everybody, even, low cost receivers, transmitters, that maybe other modulations that in the time got a little bit, away from our scope, may have an important value today.
I agree. I think that's very important, as you mentioned. Another question I would like to ask is actually related to the emerging 6G scenarios. You have mentioned there are some pros and cons on the constant envelope waveforms, but mainly because there are lack of research. For example, I have seen that you have a summary on the sensing ability, which is actually going to be a very important metric for 6G. And it's also saying that for waveforms, for sensing, it is good to have some constant envelope characteristic. And I wonder if you have known some other further research on this, particularly on the sensing performance for constant envelope waveforms.
Yeah, I mean, you're right. The constant envelope is important for the range, right? And that's what happens in radar, because for sensing, you need to go and come back. And then, I mean, there is a lot of path loss. So this is one important characteristic. But on the other hand, you need a waveform that has a good correlation properties to be able to sense. And there are some recent papers that point out that OFDM is good because it has a good ambiguity function. But I really think the best you can do is design a good reference signal. And it doesn't matter so much how you are carrying your data. What matters is how you are estimating your channel. So if you want to be efficient, you need to estimate your channel with the same waveform or pilots as you are sensing, and that's the way to be efficient. Better than maybe superimposing different signals to do different things. So we have I mean, I think all the community is now looking at using OFDM because it is clear that OFDM is going to be there for 6G. For some scenarios, you may add this precoder, decoder, so you can make it a constant envelope, or you can do the processing in the delayed Doppler domain. But having OFDM and building the pilots in a way that you can use them for the channel estimation and sensing in the delayed Doppler domain is probably the best you can do. But you're right that you still have this problem of the range. So I haven't seen, I think it is worth exploring FM-OFDM in this direction. Well, there is also, the chirp, that is chirp domain modulation or chirp domain pilots. Maybe the combination of OFDM with the chirp for the estimation and the sensing and OFDM for the data. And there are works on that already. And I think there is a need to do a little bit more. And I suspect in a few years, we're going to see a lot, in particular in our nice Multiply 6G project for sure.
Yes, thank you very much. I have one last question that I hope to have you answer. So you have mentioned that 6G is going to have some new applications, as you have mentioned. And there is also a saying that 6G is essentially a 5G on FR3. What do you think of this in general?
Well, I think there is a lot that was promised for 5G that never happened. And I think there is the opportunity to do this in 6G. And I mean, for example, related to immersive applications, immersive communication. I really want to see that. I don't know when we're going to see that. Maybe it is not going to 6G, maybe it's going to be 7. But I truly think that we have the opportunity to fulfill the needs of people to communicate further than just using the voice and the image that are absolutely fine. But the revolution that we had when we were able to add video on top of the voice is where we are today. What happened with all these video conference, people interact. Something similar can happen if we are able to add immersive video and interaction with our own body in this, plus maybe tactile, right? This requires a more powerful G that could be 6G. I think it could be because ISAC is super important ingredient for that we don't have in 5G. but also requires a lot of work. It's more multidisciplinary, so it's not enough with the radio, right? We need the people in the application that are already working very strongly on these kind of things to come up with faster encoders and decoders. Especially the video, immersive video takes a lot of latency for the encoder and decoder, and no matter what we do in the radio with our 1 millimeter, 1 millisecond latency, that at the end, this is difficult. But I think there is this opportunity, more in the applications that were not developed for 5G, and ISAC is a super important ingredient, and the artificial intelligence is a super important ingredient to be able to get what we couldn't do in 5G. And they are going to be thought from the beginning, from scratch in 6G, which didn't happen in 5G. So I'm confident we can see very, very interesting things for the people. That is where I think we should be aiming to.
Okay, thank you very much. I really like your answer. And yeah, I hope, I think there will be further questions from the audience, but I guess I will collect them and send you for emails. And thank you again, Anna, for this great talk. And I hope to see you soon in the next future times. Thank you.